topic is automatic translation of hierarchies of theories. So by theory, I mean any kind of semantically relevant grouping of declarations. So systems usually have different names for that, like locales or records or structures. So I'm going to use theory for all of that. And what I mean by hierarchy is, in the sense of category theory, a diagram. We usually start with something simple like magma, semigroup, monoid, group. And quickly you realize, oh, this is actually a tree because we have all kinds of other things like commutative, and then we can merge these again into abelian groups. Then if your system allows some kind of non-commutative diamonds, like when you build ring, when you realize you actually have two different ways to go from semigroup to ring, which do not commute, things get more complicated. And then many systems have some kind of functor-like operation, like a theory morphism, an adapter, a functor. And this is even very cyclic because you have all kinds of values. So overall, this thing we can abstract by, well, cyclic but not the commutative. Like you have some cycles that commute, other cycles that don't commute. Maybe not in this example, but in general. So in category theory, we have a diagram of theories. And this is very nice because category theory also gives us the notion of a structure between categories, which translates a diagram into another diagram. And now there are all kinds of what I call diagram operators, which you want to use to automatically duplicate this hierarchy. So this is usually on the order of, let's say, 10 to the 2 to 10 to the 3. Like you may have thousands of individual nodes in this diagram in your overall library. And there's different ways you want to translate. There are logical translations. Maybe you want to make everything finite. Maybe you want to make everything commutative. So this usually operates on certain fragments of the overall diagram. Like maybe you have one hierarchy already, then you make everything commutative, and then that becomes part of your overall diagram. There are also extra logical transformations. Maybe a notation change. Take the monoid hierarchy but make everything additive. Or maybe a renaming. If you want to handle non-commutative diamonds, maybe build a vector space, you need two universes. So you may want to take the hierarchy, duplicate everything but rename, so that you can then merge stuff together into forming vector spaces. Then things I haven't done so much myself, but in proof assistance I imagine you may want to add special techniques or technique-related things. Maybe you want to have the entire hierarchy, but now with decidable equality or something, or with a normalization operation on the terms. Then there's a whole range of operators that we get from universal algebra. You take a hierarchy like this, and you get the corresponding hierarchy of homomorphisms between two models of these theories. Or you get the entire hierarchy of sub-objects, like submonoid includes subgroup, no, subgroup includes submonoid, in very much the same way as group includes monoid. And you have language changes. That's maybe something that many people's libraries don't do, but I usually use logical frameworks where I formalize every theory in the simplest possible logic, and then very often you have to embed these theories into other logics. So for example, this entire hierarchy can be phrased very nicely in untyped first-order logic, and that should be done, because if you formalize in the simplest possible logic, it makes integration a lot easier. But then sometimes you need to use it in a bigger context. So for example, the homomorphism operator I showed here. If you want the theory of group homomorphisms, you need two universes, one for the domain, one for the codomain group. So group may be formalized in first-order logic untyped. The operator for group homomorphisms has to move everything into the typed first-order logic setting. So this would be one of these operators here, say from untyped first-order logic to typed first-order logic. And there's a lot of these. As you gradually increase the expressivity of your language, you may need to move your theories into more expressive language. There are many reasons to generate these things automatically. These are, firstly, the sheer size of the diagram, like especially as these compose. You may want to start with group, then you change the notation to additive, then you embed it into sorted first-order logic using this one, and maybe then you apply the homomorphism operator to get homomorphisms between additive groups. So if you are at 10 to the 3 here, if you have all the different ways to compose these operators, it explodes in size. The other reason is consistent style. It's very important for users, especially in large libraries, that all these theories are written somehow consistently. Manually making sure the style is consistent at that size is going to get extremely difficult. And thirdly, management of change. Very often you insert something here, or you refactor one of the series or whatever. You need that change to propagate immediately to all of the stuff you have generated here. So I'm absolutely convinced that we need to automate the process of these kind of transformations. And I've written a couple of papers on that already, but I still don't know how to best do it. So it's very easy and actually fun to implement the individual operators. But then coming up with a framework in which to do that and how to compose these operators is a much more difficult and much more annoying question. So there are 3 concrete challenges that I could think of. One is naming. All of these theories you're generating, they need to have names that the users can anticipate so that they can actually use all the generated stuff. It's really hard to do that, especially when these operators themselves might commute or get composed. The other one is when to generate. So one option is you just pre-generate everything in advance. Then you have like a very complex build process that always generates a lot of extra theories. Or you do it on demand. When the user needs a theory, you generate it. And here you have 2 subvariants. It could be that the demand is done intralogical, like have some kind of feature in your logic that allows users to call these diagram operators. Or it could be extralogical by having some kind of build script that the user calls from the outside to generate the theories that they need. And I have no idea which of these are better. And what was this third one? Oh, I think those are the main challenges I had already. So, yeah, I would like to have a discussion on more applications. Maybe there are some I haven't thought of yet. And then feedback from people with experiences with large libraries on how can we best address these challenges.
And I mean, do you know what happens with those challenges in the provers that we have this discussing about?
I think most provers don't do it systematically. There are some early solutions to having some kind of automatic generation, but I haven't seen any systematic attempts in major theorem proving.
And I mean, I've seen some attempts at kind of having the final, I mean, not final, but to have one snapshot of that, right? Like, for instance, Peter Gibson has one thing just for universal algebra, and he's not trying to do proofs at all. He's just kind of organizing one version, as I say, one snapshot, or perhaps half of some of it. Presumably there are others. Have you seen much of that?
No, I don't know that work.
Oh, okay.
So the systematic attempts I've seen, like Jacques and I have had different approaches, but we did it like outside of theorem provers. And there was one talk earlier in the workshop on doing it for lean, right? And that was also, I think, happening outside of the theorem prover, that you have a DSL to write the theory diagram and then generate a bunch of lean theories from it. That was maybe the most systematic attempt I've seen connected to a major theorem proof.
And of course, there's hierarchy builder that tries to build that diagram, but doesn't yet attempt to do this.
Yeah, right. So the hierarchy builder would probably be
That's what I
extended sooner or later.
So that's the Koch version, right?
Yeah.
The hierarchy builder, okay. Just trying to
But we
get
shouldn't
my
really
bearings.
get into the discussions now.
No, it's
you
for
know.
later. It's just kind of asking what there is, kind of.
So related to Ossio's talk about when you might have like, I don't know, different presentations of that structure, and then you want to use parametricity, for example.
Oh yeah, that was, I
that's
was
not
going to
the-
put that here on extra logical, like, representation changes or something, like bundling, unbundling, and
Yeah.
Yeah.
Okay, so that's great. Thanks, Florian. We kind of prepared